The pleasure to introduce Chiara Vercellino from the Links Foundation. So you may please connect. We can see you. Can you please start to share the screen while I introduce you? She is going to talk about near-optimal graph coloring on a neutral atom quantum computer. So we are very excited about hearing these results.
Okay.
The floor is yours.
Thank you for the introduction, and thanks for the opportunity of sharing these works that involves a class of optimization problems, that is graph coloring problems, and exploit quantum technology, that is neural atoms quantum computer. First of all, this work is part of a collaboration which involved Cineca and Pascal. Pascal is a quantum hardware provider that has a technology based on Rydberg atoms. And they provide a system in which qubits are represented by rubidium atoms, and these rubidium atoms represents the qubit. They can be mapped into a register that can take the configuration of a 2D or 3D arrays, and by means of laser pulses, these atoms can be excited in the Rydberg state. This Rydberg state is the one that encodes the one state in the computational basis, and it is the clue to map optimization problem with exploiting neutral atoms. To be more precise, the physicists that lie behind this register configuration exploit the interaction between atoms that have interaction that are based on van der Waals forces, and this kind of forces induce the Rydberg blockade effects. This blockade effects prevents two atoms within a target radius, that is the Rydberg radius, to be both in the decided state. This radius is correlated to the laser frequency, or to be more precise, also to the laser configurations. So according to the pulse configuration that we set to the lasers, we can produce different Rydberg radius. This overall effect leads to superposition and entanglement between atoms, thus providing a unit disk graph. In particular, the conflicts between atoms are obtained by looking at which atoms fall within the Rydberg radius, and thus cannot be in the same Rydberg state in the same moment. This overall behavior is described by an Hamiltonian, in which the pulses configuration are described by Rabi and Rabi frequency and Rabi detuning, but the state of the atoms are described by this variable ni and nij that represent the qubit states. This overall problem is, from optimization point of view, a MIS problem, so a maximal independence set, in which the objective is to maximize the number of items that are in the Rydberg state, so the one state, and this is obtained by a QAOE approach. So an initial configuration of the laser is set, and then a classical optimizer takes place, and the pulses configuration are optimized such as to obtain in the first position of the quantum distribution the MIS solution. This is the background to our industrial use case, that is the one from which we started to define our optimization problems, that is the PCI problems. This is a use case taken from telecommunication world, and it concerns the optimization of the assignment of this PCI identifier, and the assignment of this kind of identifier allows to provide a good quality communication to the users. The fact is that these antennas are in a limited number, and also the number of PCI that can be assigned to antennas are limited, but to assign the same kind of identifiers to neighbors antennas can highly impact on the quality of the communication. So this is quite similar to a graph coloring problems. In fact, the general problem can be translated into one or more instances of graph coloring problems. So this is why our main focus was on graph coloring problems. These graph coloring problems in general could be formalized through cube formulation, so we could exploit binary variables through one-hot encodings and represent them as qubits, such as if a color was assigned to a node in a graph that is our antennas. So if a PCI is assigned to an antennas, we have the corresponding qubits, which is in stage 1. This could also be done as the cubic matrix values correspond to feasible configuration of pulses modeling, but we have some issues. First of all, there is the fact that reflecting the overall cubometric structure into a register, such as mapping it to a unit graph, it's harder. In some cases, it could be even harder than solve the original problem. And the other fact is that using the one-hot encoding formulation would imply to use a really high number of variables, so because more variables could be needed to map to reflect the connectivity of the graphs, but also we would need 1 qubit for each antennas and for each color, so it is a very high number of qubits. Anyway, we have something that is which is plays on our favors. It is the fact that the original problem, the PCI problems, has not a random position of antennas, but antennas have their own topology. This fact implies that an inference pattern can be induced by the conflicts pattern, and this would allow us not to deal with the problems of register embedding. In particular, then we can focus on the fact that finding feasible coloring for graph coloring problems could be also mapped into finding iteratively maximal independent set for the same graph. So our approach are based on iterative MIS, so iterating the MIS solution on the natural atoms, and we propose 2 strategies. The first one is the most greedy strategy. It's a classical heuristic for solving graph coloring problems, iterating MIS solutions. In this case, we start from the initial graphs, we hold the conflicts, and we select a MIS set. The MIS set found through QAOA is removed from the initial graph. We obtain an induced graph, and we reiterate the QAO procedure on the induced graph. Thus, this until no edge remains in the graph, so there are no more conflicts. Just to simplify, I reported here a graph, an example graph. We see that in iteration 1, 4 nodes are selected, and these nodes are removed, the corresponding edge are removed, and so on and so forth. We iterate until iteration 4, where only 1 node is left to be colored, and that's where ends the algorithms, and we obtain a feasible coloring with 5 colors. Anyway, this greedy approach has just one limitation, is the fact that it looks for MIS solution at a time, so it does not exploit the quantum distribution over the feasible states. That's where enters in place our branch and bound approach. Let's represent an auto-optimization loop that concerns the solutions and no more the laser configuration. This approach relies on a theorem which says that for every graph an optimal coloring, there is an optimal coloring where at least one of the color is MIS. In this case, MIS stands for maximal independent set and not more maximum, as there is no need to be for the color to be also the one of maximum size. The branch and bound approach starts with the whole graph in the root node of the branch and bound tree, and then for at each step it branches on the MIS solution to generate other branch and bound node. And thus it iterates, exploring the branch and bound tree, obtaining multiple graph coloring solution. Also in this case, to exemplify on the same graph, I reported here the same graph as before. The plots on the left represents all the MIS solution found at the branch and bound root node, and we can see that finally we found a coloring which has one color less than the greedy IT MIS solution, and we can see also that the selected MIS solution at the root node is the one with one vertex less than the MIS maximum independent set solution. To validate the iterative approach, we exploited the state-of-art MIS solver, just because scaling up with a higher number of vertices in the graph would be not so trivial exploiting parser library. And we can see that generally the branch and bound presents an improvement on the grid iterative miss. Concerning further works, we will investigate the effect of quantum noise on the quality of solution, and we will further optimize the parameters of our algorithm, both the inner optimization loops that concerns the laser configuration and the branch and bound parameters that rule the branch and bound behavior. Last but not least, we will test our algorithm on a quantum machine, thus validating this also on a real machine. So that was all. Thanks for the attention. If you have some question, I am pleased to answer.
Thank you very much for your. Thank you very much. Okay, let me see if there are questions. I do have one. Can you please comment on your understanding about the quantum advantage and what is going to be the bottleneck with this technology concerning your problems? So where is the main issue, the main bottleneck, and can you forecast the full realization of quantum advantage on this kind of algorithms?
Okay, yeah, this can be just a nice question, and it's quite difficult to evaluate quantum advantage because we are comparing really different technology. One of the key points that we are now investigating is the fact that up to now, when the quantum machine provided by Pascal has a sample of 2 Hertz, that is quite low if you need to do a lot of evaluation to perform QA/OA and or to provide a solution in a less computational time than using a classical computer. So this is difficult. We are trying to optimize parameters as also Elisa made. We are trying to reduce the number of evaluation and the number of steps that are required to solve the MIS problem that could highly impact on the overall graph coloring solution.
Thank you. Let me check if there is some other questions in the audience.
There is a raised hand from from Sebastiano.
Okay. I can see the raised hands.
Can you see the raised?
Okay, now I do. Yes.
Okay, perfect. Very good.
Sebastian, you can ask.
Oh. Okay. Thank you. Thank you for the interesting talk. So I noticed that at the beginning of the presentation, you have mentioned that the Rydberg atoms can be also arranged on a 3D structure. And I just wanted to ask you a few more details about that. For example, if you have a 3D array, I mean, can you really create a 3D structure, and what is the type of readout that you can perform when you have a 3D structure?
Okay, with a 3D array could be used not also for the optimization applications, but also for chemistry or other fields of stimulation. Concerning the optimization, this kind of structure could help in mapping a higher connectivity of graphs. To perform quantum chains of qubits. So this is something that can be done, and yes, that's it.
Okay, thank you very much.
Okay, in principle, we still have time for another question. We can wait a few seconds, a while, if there is someone else who likes to ask. Oh, let me just ask a kind of personal question. Have you used other kind of hardware in the past so you can compare?
Personally not, but my colleagues have previously tested some hardware solution from the wave system, and we would like also to compare, see what is the noise effect, or what is generally the behavior for formulating the problem with exploiting then one machine instead of the others. In particular, we would like to investigate the difference in the solution and the quality solution by using the cube formulation, that is the one we exploit one-hot encoding, and compare it to the QA solution that instead exploits the iterative MIS approach. This is a route we are investigating.
Okay, thank you so much. Okay, so I can't see any other raised hands. So I think we can thank the speaker for this very interesting talk. And I move to the next speaker.